In this activity, you're going to be calculating the average rate of change of a number of functions. Let's take a look at a sample. Say, for example, we have a boy, and there he is. Look at him all full of mischief, throwing a rock at a window, obviously. And this is the height time graph of the rock as it heads towards the window, but notice that it doesn't actually hit it. Now, a question that we could ask is, find the average rate of change of the ball's height with respect to time from 1/2 second to 2 seconds. Now, a rate of change is really just equal to the slope of a line. Now, unfortunately, we have a curve here, and so we're going to have to calculate an average rate of change rather than an instantaneous one. Now, the slope is equal to the rise over the run. So if we can just find those 2 points, all we have to do is calculate the slope of the line that runs between those 2 points. And so we have a point at 1/2 second, which I'm going to label as A, and our second point is at 2 seconds, which happens to be right when the rock hits the ground. And to find the average rate of change of the ball's height with respect to time, all we have to do is find the slope of the line between point A and point B. And so the slope of this line is all we're after. Now, we're lucky enough to have an equation that determines the relationship between the height and the time of the ball, and we can calculate the slope directly using this function. Here's the example in Sketchpad. I'm going to bring up the calculator, and I am going to calculate my rise first. So my rise is the difference in the function at the second point minus the value of the function at the first point. So there's my change in height, and I'm going to divide that by my change in time, which is the x value of my second point minus the x value of my first point. So there, I've calculated the rise over the run, and the average rate of change is negative 2.47 meters per second. And if I look at the slope of this, what's known as a secant, I can see that that makes perfect sense. The ball, on average, is dropping between these 2 points, even though it goes up for a portion of the domain of this function. On average, it's dropping, and I can see that the slope is negative 2.47.